This is the second section of the chi-square test chapter, and here we're going to be looking at degrees of freedom and the chi-squared family of distributions. So you remember from the previous section that we did, we worked out this value of x squared, and remember, like, the easy way to do it was x squared equals I won't bother using the sort of I notation, but basically for each observation we square it, we divide by the expected observation. So we do this for each column, and then we take away n, which is the basic number of observations, observations like that. Not enough space. Look at that. A triple word over 3 lines. Okay, and what we said was, what this gives us, it gives us this number, which is almost like the variance, or the let's call it the variance of the observed values compared to the expected values. Yeah, so we're working out the difference between these observed values and the expected values, and you know, we'll get some sort of number. So if the difference, if this value of x squared, which gives us the difference between the observed and the expected, if this was sort of a large value, okay, that means there's a big difference between the expected and unobserved. That means basically our data doesn't really fit the expected distribution well. So I would say, like, not a good fit. Yeah, and that's when we would reject H0, because H0 is, yeah, it basically fits the distribution. And if x squared was small, then we say, well, it is a good fit. It is a good fit to our expected distribution, and then we would accept H0. Now, just saying large and small here, that's not particularly helpful, because who decides when x squared is large? Who decides when x squared is small? We need to compare it to a value, and this is where chi-squared comes in. And chi-squared is this Greek letter like this, chi-squared, and what we're going to be doing is we're going to be comparing our calculated value of x squared, and we're going to be comparing it with this chi-squared. And chi-squared is what we call a family of distributions, and below in this little graph here, you can see lots of different curves drawn. They're all chi-squared graphs and or distributions, and you can see that, like, they're all slightly different, and it's got this df equals different numbers, and df stands for degrees of freedom. So df equals degrees of freedom. So basically, if we have a different value for our degrees of freedom, which we'll talk about in a moment, you'll get a different shaped graph. So for example, if my degrees of freedom is 3, then you can see that this is the graph that I get. And what this graph of chi-squared, what this allows us to do is, for a particular significance level, is compare our computed value of x squared with chi-squared, and then decide, do we accept or reject H0. Our chi-squared distribution is going to help us decide whether x squared is too large or it's too small. It will help us have that cut-off point number that comes in. The next section is actually now doing a hypothesis test with it. So how do we work out these degrees of freedom? So let's say, for example, I had a table which is with dice, and let's say the outcomes are here. Let's make it easy, 4-sided dice, 1, 2, 3, 4. And in the bottom row of this table, I'm going to put the expected outcomes. So let's say, so this is not probabilities, this is how many times I expect this to happen. So this is not what I've observed, this is what I expect. And let's say it's, we roll it, I don't know, 120 times. Yeah, but this is not a fair dice. So let's say that I get, this is 60, this is 20, this is 10. So what have we got to now? 90, and this is 30. Okay, so these are the number of times I expect this to happen. Now, if I roll my dice 120 times, if I fill in those 3 boxes, then the last box at the end I can work out, can't I? Yeah, so if this box and this box and this box are filled in, and I know I'm doing it 120 times, well then I know that to work out this box I need to do 120 minus 60, 20 and 10. So in other words, 120 minus 90, I know this box has got to be 30. Okay, so this box has to be 30. Okay, we have no choice. And this is what we call degrees of freedom. Yeah, so actually we have here what we call 3 degrees of freedom, because this can move around, this can move around, this can move around, but once those 3 have been written down, this box is fixed, because I've got to work out that box by subtracting the others from 120. So we say that here we have 3 degrees of freedom, and you could write that as 3df, 3 degrees of freedom, because the first 3 boxes, they can be whatever values you like, but once those 3 numbers have been written down, the 4th box, well, that can't move around to whatever it's like, it has to be whatever's left from 120. So if we go up to the top here, we've got a little formula, and the way that we work out the number of degrees of freedom is the number of cells after combining, and we'll talk about that in a moment. So here you can see that there were actually 4 cells here, 1, 2, 3, 4 boxes where I can put the expected frequencies in. And the number of constraints, well, this is 1, yeah, because that box, that has to be as a fixed number. So we could just do 4 minus 1, and we get 3 degrees of freedom here. Now, what does it mean by after combining? Well, it may be that our expected frequency is less than 5. Yeah, if we have any expected frequencies or values that are less than 5, we have to combine those frequencies, combine those boxes in the table until they are greater than 5. Yeah, so that's what this after combining means. Any cells where the expected frequency is less than 5, we have to basically clump them all together. And last thing before we move on, degrees of freedom, we have like a little letter here, and this is the Greek letter nu, pronounced like that, nu, that's how it's pronounced, and that is where we would put the degrees of freedom. Okay, so if I saw something written like this, okay, that means 5 degrees of freedom, and these values we can look up in a table, and the value that we look up in a table will give us the cutoff point of when we decide when the x squared value is a value that's too big, which means it doesn't fit the distribution, or it's small enough to say, well, it's close enough to the distribution, that our variance is small. So this value that we look up in a table for this will give us the cutoff value at which we decide basically whether to accept or reject H0. Okay, so in a sample of 100 households, the expected number of dogs, and so we've been given the expected number, so remember this is not the observed, but the expected that we use to get our chi-squared value. Here we can see that in this table there are 1, 2, 3 cells here where the expected values are less than 5. And remember that we need to combine any cells where the expected values are less than 5. So we've got 3 of them here, and it says select an appropriate chi-squared distribution to model the goodness of fit x squared for this data. Right, so let's so we've got dogs here, and we've got our expected frequency here. So the 0's fine, that's more than 5, so that's fine. The 1, yeah, and the 2, which is 10. So all of these expected frequencies are more than 5. But then the last 3 are less than 5. So I add those together to create a frequency which is more than 5. So that will give me 8. And that is the number of dogs which represents 4, or actually more than 4. Yeah, 4 or more. So let's write that down. 4. Well, I could do greater than or equal to 4, couldn't I? Like that. Or I could write that as more than 3. Doesn't really matter. So this is what we mean by combining cells. So after combining the cells, I have 4 values that can move around. One of them can't, yeah, because once you've got the 55, the 20, the 10 and the 7, and we know that the total is 100, so let's put that in. So total here 100. Yeah, once you've worked out these, then basically the last cell here has to be equal to 100 minus the other values. Yeah, so we have one constraint. So the number of cells after combining is 1, 2, 3, 4, 5, with one constraint, be that last column has to be whatever is left from 100. So the number of degrees of freedom is 4, so we can write nu equals 4. So this can be written as chi-squared with 4 degrees of freedom. That's how we write it as that. So what that means is that an appropriate chi-squared distribution to model the goodness of fit for x squared would be this. So x squared approximately chi-squared with 4 degrees of freedom. So that would be our answer for this question. So in this example, it says with nu equal to 5. So this represents our degrees of freedom. So we could say we've got 5 degrees of freedom. Or you could write that df equals 5. Find a value of chi-squared that is exceeded with the 0.05 probability. So first thing we need to do is have a look at how this table works. So the first column here gives us the number of degrees of freedom there, and we are interested in 5 degrees of freedom. So we're only going to be looking at this row of the table here, and we're looking for this 0.05 probability, which is here. Yeah, and that's a bit like our significance level. So if we have a look in this column, it's like 5% significance level, then we get this value here. So I can write down that chi-squared with 5 degrees of freedom at this 5% level is equal to 11.070. Now what does this mean? So it basically means that when we calculate x squared, if our calculated value of x squared is greater than 11.070, what it means is that our observed data is too far spread from the expected data. So in which case that our observed data isn't a good fit for what we expect it to be, in which case we would reject H0, because H0 is our data is always a good fit for our data. But if x squared is less than this 11.070, so this is like a cutoff point, which basically means that our observed data is close to the expected data, then we would accept H0. So this is how we use this table. It's going to help us decide when to accept and reject H0 based on the value of x squared that we've calculated. Right, so for each one of these we need to find the critical values. So in part A, first part of part A, we have chi-squared with 3 degrees of freedom, and we're looking at 95% significance level, and that means we need to be looking in this, whoops, not that column, that's 97.5%. 95% is going to be this column, and the row we're going down to is 3, so that's this value here. So we have 0.352. Second bit of that question, we have chi-squared, 4 degrees of freedom, and 10%. So let's rub those out and let's change it to 10%, which is going to be this column here, and 4 degrees of freedom, which is going to be that row. So that gives me this value here. So I'll try that down at 7.779. Then in part B, this is just a slightly different way of wording the question or using the table the other way around. And we're going to find what this probability is. So it's the same as the first part A basically, but just different wording. So we have the probability that chi-squared with 2 degrees of freedom is greater than y at 95%. Okay, so the smallest value of y, so we look this column here, 95%, so we look at this row here, so that's going to be our value. So same as the first part, just the question has been put in a slightly different way. So the value of y, 0.103. So you can think of these like our critical values, yeah, just like we had critical values before with other distributions. So the second one, it's chi-squared, 4 degrees of freedom greater than y equals 0.99. So we just need to find a value of y. So let's rub this out. So this time we're looking at this row, 4 degrees of freedom, 99%, which is this row here, or column. And so that's going to be our value of y. Y is equal to 0.297. Right, you should now be able to do exercise 6b on page 99. So you will need the table in the book on page 192, or if you're using the table from the formula book, you'll find that on page 36. Okay, and remember that we have this chi-squared distribution with nu here, and this represents the number of degrees of freedom. And once you have your degrees of freedom and you have your like significance level, so you're going to have some sort of percentage in here, yeah, you can then easily look up values in the table.